AI, you might have heard about it. It stands for artificial intelligence. It's basically everywhere today. And we're web people, right? So we also want to use AI. We don't want it just to be native app, everyone having to rewrite all the experiences to a native app in order to benefit from all these new features. So first, a little bit about me. I'm apparently supposed to introduce myself. So I've worked on browsers for more than 15 years. Started with WebKit, moved on to Chromium. I've worked on a lot of different standards. WebNFC, Wakelog API, progressive web apps, cookie storage. I don't even remember. I've also been on the World Wide Web Consortium Technical Architecture Group for 4 years. And as other people, I'm a Google developer expert and Microsoft MVP. So here's a video. So I worked on this browser for Nokia called the N9 browser. Oh, there's actually music. So this was my first big browser product. It was actually quite nice. It got pretty good review, and a lot of people on my team actually ended up working at Apple on Safari. Unfortunately, this guy came from Microsoft. He took over and said, let's do Windows Phone. It's kind of boring. It meant that I didn't have a job to do because it already came with a browser. So I had to leave the company, and I went to a semiconductor. And you might be wondering, like, semiconductor, what is that? Well, we do hardware, we do chips, even AI accelerators. So if you look about AI today, a lot of these big, huge models, they run on data centers. So that means there's a high cost. You have to pay for all the inference running on those data centers, in addition to actually training and creating the models. There's also high latency, because your data center might not be right next to you. So you have to send data over the wire. It needs to get the answer back. And there's lack of privacy, because whenever you're sending something over the wire, it could be intercepted somehow. There's always some challenges, privacy and security issues in that area. So this is our ex-CEO. We just got a new one. But he came up with these like 3 laws. So like, we have the law of economics. As it costs you money, it would be nice if all those AI inference could run locally, because then you don't need to pay for it. Your users are just using the CPUs, GPUs, NPUs to run all these inference cases. There's, of course, the law of physics. The closer it is to your hardware, the faster it's going to be, especially around latency. And, of course, the law of the land. If you're in Europe, as we're right now, there might be regulation that this cannot be. You cannot store all those data in China or in the US. Things are changing rapidly. So this means that everything is moving to client. So Intel, together with others, introduced like a whole new kind of way of doing like CPUs that comes with an NPU. We call it the AI PC. You might have heard that Microsoft have this brand called the Copilot Plus PC. It basically means that every PC running Windows going forward to get this branding will have to come with a quite capable NPU. So you might know the CPU is the central processing unit. Then you have the GPU, it's the graphics processing unit, and you have this new thing called the neural processing unit. So it's basically if you have like AI that normally all the data, all you're preparing is running on the CPU. So if it's like a very simple case, it's often faster to actually run that directly on the CPU. If you want the best throughput, the GPU is normally what people are choosing, because you have dedicated hardware. It can run a lot of things in parallel. That's really great for high throughput. But you also want like great battery life, all-day battery life. So if you just want like background blurring, you don't want it like to use the GPU and suddenly you only have 2 hours of meeting time, where normally you can use your PC maybe for 10 hours. So this is why we have the NPU. What we don't know is that maybe with time, the NPU might actually become so good that it will take over some of these other use cases. We'll just have to wait and see. So you might be wondering, what is the web angle? Well, the web angle is that the web is really great because it's this ephemeral platform with low friction. Everything is just a URL away. Type in a URL, you click on the URL that comes maybe from your WhatsApp, and there you go. No waiting time, no loading. It's an instant experience. That is the low friction. But also, if you don't use this web app for many years, Well, it's like your system is going to be overloaded, you're loading more and more websites, and that website is going to get removed from your system. All the caches are cleared, you always can load new web pages. This is unlike what often happens with native apps. I even looked at my phone, I have so many apps because you go to one country and you need to pay for parking, and they're like, oh, you have to install this app. So you install that app, it keeps updating. Years after you haven't been using it, it's still updating. There's a new feature on Android, though, that at least removes the permissions if you haven't used it for a while. But the apps usually just stick around. And I never have time, I don't even feel like going through my system to figure out what should I remove. That is not the case with the web. Another huge advantage is that it's cross-platform. So you write a web app, you can reuse it for your Windows PC, your Chrome OS PC, your Android device, your iPad, basically everywhere. And it's a pretty approachable platform. We have great programming languages as JavaScript or TypeScript we just heard about this morning. That is making it really approachable. So there's a lot of developers out there, like you. So this has been a quite winning strategy for us. This is old data. I need to update it. But last I checked, we had 17.4 million JavaScript developers. That's a lot. We also have some statistics from Intel, let's dig into that a little bit later, that says that around 65% of CPU cycles, that's the time you're using the CPU, is actually just running web browsers. So it's growing and growing. And if you look into the data, it's kind of interesting. You see the #1 app on Windows is Chrome. So that's Google Chrome, that's a web browser. The second one tends to be Microsoft Edge, that is also a web browser. Third one is Firefox. You see a pattern here, it's also a web browser. Then we got Outlook. Outlook is actually a progressive web app that is wrapped in what they call the Edge WebView 2, so it's also kind of the web. It's not counted as a web browser. Then you got Internet Others, there's other web browsers, like Vivaldi, Opera, Brave. Then you have Excel and Word, and those are also becoming web apps. So if you embed Word inside of Microsoft Teams, it's actually running as a web app. So basically, if you look at all of these data and count Electron apps, these semi-web apps, you get to something 85, 90% of CPU cycles. So the web really matters for us. So this also means that we have this saying at Intel that no silicon left behind. We might dedicate a large portion of a CPU for an NPU, but if you as developers cannot use it, if you have to write a native app for that, and you see that maybe more than 80% of the time is just running web, that silicon is being left behind, it's not being used. And you, as the user, you're paying for that system, for something that you cannot use. So that's not good. So the world runs on software. We need to make sure that developers can take advantage of it, of all the hardware. This is something we've always done at Intel. We've always been working on standards, collaborating with Microsoft, Google's standard organizations on Bluetooth, Wi-Fi, etc. And we keep on doing this. So in our team, we have this saying that we want the web to succeed. We want the web to become an unquestionable key application platform, something you can use not just for creating websites, but for actually creating web experiences. But we also don't want to fuck the web. The reason why I'm saying that is because I worked at Nokia and other places where people always had this idea that we should just take the web and we should make these installable web apps. You should take the zip file and you install it as a web, or you do Electron. But the problem when you do that is that you remove the advantage of the web, like the low friction, that everything is just a click away. You remove some of the safety and privacy need because it's installed, so it's trusted. So we don't care about Bluetooth. You can access everything. We don't need to do that. And I've seen that fail again and again and again, which is one of the reasons why I started working on progressive web app back in the days. But how are we doing? We're actually doing quite well. We have apps that are progressive web apps. You can install them. You can make even immersive 3D apps. There are a lot of WebXR APIs. We've worked on a lot of things for just making web apps work really well. You have probably seen the View Transition API that makes all these nice transitions. There's web animations. We have service workers. There's new APIs coming like the Navigation API that makes it much easier to do routing. It even comes with a URL pattern API, so you do the matching much easier. I even made a polyfill for that, URL pattern. It has more than 10 million weekly downloads on NPM. So it really seems that's something that people like to use. So we keep on doing this. And that's what we're doing at Intel. We've been working with a roadmap team to try to figure out like what is coming up in the coming years and how do we support you. So one of the things we're working on is like Project Fugu, or Hygge, we call it in Japanese. So we've been trying to, first of all, like look at the web, like what are all these APIs that people are using? Can we build in some more like native apps, native APIs that allows you to do the same? Kind of explain the magic. Really reach out to developers, going to events like this, talking to developers, and finding out what do you need, and how do we do this in the best way possible. With Project Fugu, we actually collaborated with Google and Microsoft, even like Samsung and Electron, on like figuring out what we needed on the web for the web to succeed. So one of the things we got is that a lot of people said like, yeah, it's really cool, I really want to build this web app, but I'm needing this one API. If I don't have like Bluetooth, I can't build a web app. I need to do native. I need to do some kind of hybrid where I do it myself. And then I lose all the big advantages of the web doing so. But the other problem is that it's really cool that you, like Chromium, you go and build in like Web Bluetooth API. But what happens like in a year from now when I have this other API that I need? Like, can I trust the web to always have the APIs that I need to build my experiences? If I'm a company and I decide to bet on the web and I'm making a great success, but my competitor builds a native app, and then a year from now at one of the big events, Microsoft or Apple or Google announces that this new API, say AI, and like I can't take advantage on the web, but the native guy can just use it from day one, and suddenly I lose all my users. So we need to make sure that we have a roadmap, that we always come with these new APIs. And that was kind of one of the ideas behind Project Fugu. Identify all the gaps on the web platform and implement those APIs, and have a roadmap for always looking ahead and implementing whatever comes up. So we had a lot of success with that. One of the APIs that people have been asking for forever was a file system API. So today you can go to vscode.dev and you can basically run Visual Studio Code in your browser. There's a few other APIs that I've been working on to make this work even with the plugins, but let's not get into that. Another example is Photoshop. Photoshop used to be the #1 app that I said, this is the one app we're never gonna get on the web. Because think about it, you're having this 8 GB big image and you're using it on the web and you have all this effect, never gonna run on the web. And yet here we are. This runs in the web now. They're actually using a special version of the file system API called the Origin Private File System. So it allows an origin, like a website, to create it like a swap file or like a hidden file. It has some APIs that makes it faster because you cannot access it from your Internet Explorer or like your file system Explorer or whatever. And that allows them to do all this like swapping out of data if you have big images. We worked on something called SIMD. Probably not a lot of people that know that. It stands for Single Instruction Multiple Data. So on the CPU, you know we have instructions. So you have an instruction saying, take this number, multiply it by this number, and put the result in the register. You also have instruction that does the same maybe for phone numbers. So take this vector of numbers, multiply this vector of numbers, and store it down. And that's, of course, much faster. Imagine going over an image. Every pixel is normally red, green, blue, and alpha. So you can do this in one instruction now. And by using that in Photoshop, they had a case where they got 160 times speed up. But on average, they got a 4 times speed up, so pretty good. And this allowed them to actually run Photoshop on the web, also using technology called WebAssembly that allows you to support existing C++ code, Rust code, etc., and run it on the web. Here's another example. So this is from iRobot. They have this education tool called Root. I believe it's like a pen you have in the middle, and you can program it as a kit, and it can draw on paper. It's really cool. And of course, for this to work, you need to connect with it using Bluetooth. And now they have the Web Bluetooth API. This is possible. But when we do this, this is the web. It's kind of like the World Wide West. It's very dangerous. There's always people lurking around trying to abuse you and attack you and destroy your privacy. So you can imagine if every website has access to all Bluetooth devices around you, they could pretty quickly identify that we're at JNation right now. And say, aha, okay, this is probably that person that could track you. So what we did on the web with Bluetooth is that they don't know what Bluetooth device around you. What they do is that they allow the user to select a device. But you probably don't want to show 1,000 different Bluetooth devices, so you can also set a filter. So I just want to connect to this very specific root device, and it will only show those devices around you. When you click on a specific device and press connect, only that connection is shared with the website. But we always have to be innovative and figure out how can we abuse these features, and how can we make sure that that's not possible. Our current focus at Intel is been for a while. It's been focusing on capabilities, improving what's possible on the web, as well as improving the performance, making things run faster on our silicon. And today, AI bridges those two. So today we're going to talk about a few APIs we've been working on. First of all, WebAssembly that allows you to take existing code and a native code and run it almost at native speed in the web browser, in kind of like a sandbox. You have WebGPU bringing the newer modern GPU APIs to the web, almost the same performance. We have the Web Neural Network and new API that wants you to run AI models inference directly in the web browser with your own models, running on CPU, GPU, and NPU, as well as something called compute pressure that allows you to monitor the system's performance. Am I doing too much? Should I stop doing less to get a good performance? And we'll look at that later. During COVID, we saw a lot of usage in online meetings. So this has been a use case that has been driving, especially laptops. All of the features we've been working on is a lot of focus is on meetings and Teams, Microsoft Teams, Slack, all of these. And you saw that during COVID. Something like Google Meet got a 30-time increase in usage. A lot of people are using, Zoom went from 10 millions, and this is less than a year, to 300 millions. So you can understand a lot of focus has been going on improving this. This is one of the examples of how we're working on performance at Intel. You saw a team that got 20% longer battery life for Teams and Meet. YouTube now runs as fast in the browser as in the native app like an Android. And Zoom got this 75% video encode latency reduction. The way we've been approaching is that, for instance, we looked at what are the areas we would like to improve, like connectivity, latency, smoothness, battery life, identified existing APIs, or invented new ones. So one of them we worked on was web codec. So it happens to be today that a lot of the CPUs actually come with dedicated hardware for encoding and decoding a video. So this is the reason why you get all-day battery life on your iPad to watch videos, because it's not really using a lot of CPU for that. It's just using those accelerators it built in the hardware. The problem on the web is that you couldn't really do that, or maybe you wanted a different resolution, you needed a different protocol, you need to change things, and doing that, we didn't have APIs to do it. So what people did is that they took FFmpeg to use WebAssembly, so they ported FFmpeg to WebAssembly and ran that directly, and battery life just went down. So here we worked with Google on actually creating a new API that allowed people to directly talk to that hardware, resulting in much better performance. And now let's look at AI. So one of the examples, like I said, AI can run on the CPU, the GPU, or the NPU. So on CPU, it's obviously going to be WebAssembly. So here we have WebAssembly, and I just talked about the single instruction mode data. So most hardware out there today, from Intel and our competitors, at least support this of vector size 4, 128 bits. So this is what has been standardized so far. But at Intel, we have hardware, almost all of our hardware will support double the vector size. But you cannot use that on the web. So here, as in the performance improvement, we went and automatically, on the fly, converted some of these instructions to 256-bit SIMD. And just by doing that, we got at least a 20% performance improvement. And even in one case, you see more than 50% performance improvement. So that is one of the examples of how we improve performance. Now we're also working on standards on actually bringing native support for these bigger vector sizes to the web. WebGPU. A lot of people don't know that Intel has been one of the companies really investing on web GPU. It was originally, I think, a proposal from Apple. Then they kind of like backed down a bit. Then Google took over. Everyone looked at it. And Intel said, let's make this happen. So you see, it's been a long journey back from February 2017 until like 2 years ago. It actually shipped in Chrome. And you see there's a lot of different adapters, like TensorFlow will be using it, Google Meet, Photoshop. Everyone is basically using Web GPU today and getting better performance. But the cool thing about Web GPU is that GPUs originally had two kind of shaders. That's something called a vertex shader, because everything is triangles. So you work on the triangles, on the corners, the vertices. Or you had a pixel shader. You went through all the pixels in the triangle. But then people found out, like, hey, it's kind of nice, this hardware. It's very simplistic, but you could use that for math, right? Because you have so many different cores running in parallel. So this would be really great for computations. So people created compute shaders. You could not use these in Web GPU, but we have provided those in WebGL, but they work with Web GPU. So now you can use that as well. And that meant that, for instance, Intel contributed the backend for TensorFlow.js. So that is something we have done. And this is like very old data. I don't have an updated graph. But you see that across all these tests, you're seeing better performance. There was one test initially that was not faster, but that is also faster now. So really a performance improvement for the web, and really allowing people like TensorFlow.js and all these other experiences to use that hardware and run it faster on the web. So here's one example where we're actually doing some Gen AI on the web. And so this is just in the web browser. But there are different ways of doing AI. There's also called like built-in AI. So if you look down here, like you have the hardware, you have like the NPU, the GPU, CPU, then you have like native APIs. So I think like Windows now has moved over to something called Windows ML. So that's a new phone that they announced that I think last week, so I need to update the slide. On top of that, you have the web browser. Then you have these like the WebAssembly, Web GPU, and something called WebNN, Web Neural Network. Then you have the frameworks, normally what you'll be using. But you could also sometimes just use something even higher level. Sorry. You might have like an API saying like, hey, language detection or translate API. So we've been working on these higher level, or we are working on these APIs right now. Some of them was announced like last week at the Microsoft Build and Google I/O. So I haven't talked about those yet because I was waiting for them to announce it, not to steal the thunder. But other ways to use this is something like taking existing APIs. Like you have a camera, you have WebRTC, it's used a lot in meetings. Maybe we could use AI in the background and just like accelerate these use cases. So here are some examples. So we looked at actually at WebRTC and asked developers, so what do you need? Well, we kind of need face detection, so I can do funny hats, maybe some autofocusing, face framing, if like I move around a lot, so maybe the camera would be following me. People tend not to look in the camera, so maybe I can correct the eye gaze, noise suppression, all these things. And we came up with APIs and implementation to improve this. So here's one example of using background blurring and run that actually on the hardware directly. So that is using like AI acceleration in the background. And the API, I don't know if this was the final API, but like it's just basically like a few lines of code, just like, I need this feature. If it's available in hardware, it'll just do it automatically. So here you see, this is like Chromium power usage, not using the feature. If you were to use like TensorFlow, there's something called BodyPix, you see, it uses a lot more, 2.5 times the amount of battery. And even with what Google is using in Meet, with their media pipe GPU bokeh effect, you see that's the same. With our implementation, we just get like, I think it's 10, 20% more battery out, just for getting background blurring. With face detection, something our team has worked on for a long time. Original, we tried with OpenCV. It was pretty huge, 8 megabytes, a lot to download. Google's media pipe, they do the same with 2 megabytes. We tried something called shape detection API that never became a big success. And now with WebRTC, we do the same. So this is just like natively implemented, hardware accelerated, and you can even make it detect more than one face. So see, my colleague will be joining soon. Now he's joining, and suddenly we're detecting two faces. Same thing, one-line code change, basically, and you get that feature. We've even been working on seeing if we could expand this to get like the contours, so you could do like funny faces and all of that, without even having to implement it or use your own models. We can just ship the best model that exists for a specific device. And just as before, performance is excellent. Same thing, a lot of cameras today, they actually support in hardware the panning, tilting, and zoom. So we made APIs for that some years ago, but why not just do that automatically? You can just have the camera follow you around. All powered by AI and the native hardware. Same with the eye gaze correction. Gen AI, right? We can modify everything, so why not just modify the eye so it looks like you're actually looking at the camera? Yeah, it's a bit scary, but same thing with like all the optimization, saturation, color, temperature, you can just do it automatically, just like that. And this brings us to the Web Neural Network API. So this is not the built-in APIs, but if you want to do something different, where you want to bring your own models to the web, we have this new API we've been doing it for a while. It's standard. It works across CPUs, GPUs, and NPUs. And you can bring your own model. So this was announced like last year at Microsoft Build, and it's in a developer preview on Windows.
But introducing WebNN on Windows.
Yeah, the sound is very low, so let's just skip that. But here you see the same. The yellow one is like native speed of running one of these models. The blue one is just using WebGL. And you see with the light blue one is using the WebNN. And as you get very, very close to native speed using this API. Here's another example. You see native speed, WebAssembly almost the same. Just using on WebAssembly very slow. Doing all kinds of optimization using threads in the background, using SIMD. You get it slightly faster, even like a 3-time increase. But still, it's far from native speed. And here you see it on CPU, it's like 93 times native speed. On GPU, it's 83. These are old numbers, probably better today. And even on NPU, it had like 80. This is like really early work, but we're going to get close to 90, 100%. And it's a developer preview, so like there's some examples here. So all of this is just running directly in the web browser. So this is on an Intel GPU. And you see you can do object detection, and you see like the 50 milliseconds. It's pretty fast. That just runs locally. Of course, the problem with the web is that you need to bring your own models, so you cannot have the biggest model. You could, in theory, but a lot of people don't want to go to a website and say, hey, let's just download 5 gigabytes of models before you can do anything. So you have to think about that. Here's another example of generating, so Gen AI, so we're generating cats. A cat under the snow with blue eyes, covered by snow, cinematic style, medium shot, professional photo. And you see it's pretty fast. And you can even go and change. So let's do a tiger instead. And there you go. Now we got a tiger. Really cool. So, really nice. There's a lot of demos. I'm going to share some links at the end so you can take a photo if you want to play around with yourself. Unfortunately, without sound, this is actually using 2 different models. So they're using a model for detecting speech, turning that into text, and then they're using a large language model. Yes. They'll actually go and respond to that. That was a collaboration we did with Khan Academy. And you see all of that is running with WebNN on the NPU, and you see the usage on the NPU there, the power usage. So pretty good, very nice. So to sum up, there's 3 different ways to run like your own models on the web. You can use like CPU only with WebAssembly, GPU only with WebGPU, or you can use the new WebNN when it's shipping everywhere on all 3, CPU, GPU, and NPU. So it's in a developer preview today. So you can go turn that on in Edge or Chrome, and you can try out all these demos. It's pretty cool, and I encourage you to do that. and give feedback. Something else I've been working on, we actually shipped in Chrome now, is the compute pressure. So this actually came from people like Zoom, like the companies. It's like, think about this, like you use Netflix. And what is the most annoying watching streaming is if you get like a waiting sign, like, hey, the bandwidth is pretty bad, so sorry, let's wait a second. Oh, no, it's gone, the movie's on again, and we take a break. So what streaming companies do is that they look at the bandwidth, and they say, the bandwidth is going down, so we just lower the resolution a bit. You can still watch the movie. Maybe the quality is not the same, but at least you're not getting interrupted. So a lot of like the meeting things, they do the same with CPU. They say, how's the CPU or the GPU pressure going on? So if there's a lot of pressure on the system, maybe it starts stalling a bit, it doesn't pick up the microphone. So instead they say, let's just turn off some of those features. Let's turn on the background blurring. Let's turn off the camera for some people. Let's only show 4 people on the screen. There's a lot of things you can do with that data as well. Unfortunately, the thing on the web we talked about before is like privacy and security. So with global state, you can quite easily identify a user because if you have multiple websites running on the same system, getting the exact same state, they can identify you as being that same person. That's why we have fingerprinting on the web. So trying to come up with an API where you get like enough data that is usable, but don't get all the fingerprinting, make sure that you cannot use it for side channel attack, is kind of difficult. We came up with having 4 different states. Nominal, not much going on. Fair, like there's some people using the system, it's going fine. Serious, yeah, okay, there's a lot of users on the system, but we're still doing great. Critical, yeah, it's about time that you do something to make sure to lower the pressure on the system. So this is a small demo I did. So I made this like a very nice view of emojis. It shows the system's pressure. And I add some workloads by doing Mandelbrot simulations. I'm just adding more and more workers, web workers. This is on a low system. On my desktop, this doesn't even change. But you see, like, as I'm adding more workers, the pressure goes up. It even goes up to serious, like critical. And then if I lower it again, like it gets, or stops it, it gets quickly, it's recovering and feeling great. And you can see I can do that again. So that's kind of like the API. Very simple API, allows people to change what they're doing if the system is under pressure. But we talked about privacy. So when we, in the W3C, you're doing a standard, you go for all these reviews, and we had to send our API to something called the ping. It's a privacy interest group. And the VP for privacy and security at Brave said like, this can actually be used for a side channel attack. Imagine this. You're on a website you're not supposed to be. Let's not mention the name of this website. But they collaborate with this other website. So for instance, while you're on this website, one website is going to like try to modify your CPU usage, and they're going to broadcast your user ID. So this means that the other website can intercept that, identify you as being the same user, and share data. So maybe now suddenly you go on Facebook and suddenly you see ads for something that you are not supposed to see ads for. So I was like, is that really possible? So I went ahead with JavaScript, and I actually implemented an algorithm that was trying to do this, modify the CPU usage and do an algorithm. And you saw that I was just trying to broadcast hello world. In many cases, it was it even succeeded. And by repeating this over and over, setting like the position of the characters with time, you would broadcast that user ID. Very simple API. I had like the 0 state, like the 0 bit is like when it's nominal fair pressure. Critical was a 1 bit, and I have like a reset in between to make sure that it knows when I'm changing. And then I send like the position and a checksum, so the checksum I reversed, so that way if it got out of alignment, I could realign the data stream. At the end, we came up with 2 solutions for actually fixing this problem, like mitigating it. We implemented this in Chrome, and we actually finally passed the security review and privacy review, and it's shipped in Chrome. So it just shows you all the trouble we go through on the web to expose these features and make sure that it's actually safe for your users. So if to summarize, like at Intel, we're really working on empowering this AI PC on the web and all these future experiences. And if you want to take some pictures, here's some of the slides. If you want to try the new APIs, you can take a few pictures here. I saw a few people. And here also, like, we try to put all those cool AI demos in one website. So that's also really cool to check out. And yes, I work for Intel. We have to show this, unfortunately. But as I see, we have a bit more time. I think we had like 15 minutes. I'm going to show some other of the cool stuff we're working on. Because at Intel, we don't just work on AI. We really work on empowering the web and web experiences. So this is my coworker, Alexis. He's really good at making demos. So you've probably seen all these foldable displays. They're really cool. So we got a few of these at Intel as well.
My name is Alexis, and I'm here to tell you a little bit more about the work that we've been doing to improve the foldable devices on the web. So here's a little example. I have this gallery demo where you can scroll through your pictures, and then if you select one, then it opens it full screen, trying to use the available screen estate to show you the picture as the biggest size possible. That was great. However, when I undock the keyboard on the foldable device, I have this extra screen estate that comes down. But then, because the gallery hasn't been adapted for them, then you can see that it tries to lay out the picture in the middle of the fold, which is not really a great user experience, especially if I use, for example, a portrait picture that looks very odd. Now, I have the same demo, but with the APIs turned on, and for foldables, we have adding 2 new APIs. So the device posture API, which allows you to get the overall posture of the device, how's the device being used, as well as the viewport segment, which tells you information about the top section, the fold section, and the bottom section. So for that same demo, if I, for example, select a picture, you can see that now we lay out the picture on the top section of the screen, which is a lot better. Here's another one in portrait, which is what the user would expect. Now we went a little bit further on this demo, and then when we use the device in book mode, then we provide actually a split UX. And you can see here, I can select the picture and then it shows on the right with extra information, right? So that's a playful way to improve the user experience. And I have another demo that actually embraces the form factor. So I don't know if you're probably familiar with this little demo, which is the fold ship demo. It's like the battleship when we were young, where you have your enemy fleet and you have to try to find them, and then you have your own fleet. So in this case, I'm a bit limited in terms of screen estate to display extra information. I have to basically display the most important part of the game. Now, with a foldable, I have a lot more screen estate to play with, and I can do something like this, where I put the bottom section as your own fleet, and then the top section as your enemy fleet, just like the actual real physical game. And I use the fold section as a playful area to display extra information. Another demo that actually leveraged the form factor is this one. So this will be a typical news website, right? You scroll down with articles and pictures. Now, if you rotate the device and read in book mode, then you can see that I've created a paper quiz imitating a journal. And then if I put the device in flat mode, and then it changed the layout, and then if I deploy the kickstand, then I can have like the actual normal screen layout, right, with no fold. And if I fold the device again, then the paper quiz will appear again, right? Thank you for watching.
Yeah, it seems that we're having some problem with the screen. Anyway, thank you very much for coming and listening to this talk. And if you have any questions, I think we can take a few questions now. If not, you can just find me through the conference, and I'm willing to chat.
Microphone. Yes, so we have time for questions, and then we're going to have Josh's book signing. So it's about to start. So anyone has any questions for Kenneth right now? There's one there.
Oh.
Thank you. Thanks a lot, Kenneth, for the presentation, first of all.
Sorry, I cannot hear you.
You can hear me? Is it better?
This is better, yeah.
Thanks a lot for the presentation, first of all. You mentioned, when you were explaining WebMM, basically examples of benchmarking on usage of LLMs, but artificial intelligence in general, artificial intelligence models in general. Do you have any sort of benchmarks for training using this WebNN? Or, is this a usage that you're pursuing for training new models or for doing custom models? What's the current state on that? Can you elaborate?
It's a bit difficult to hear, but are you asking about benchmarks for like WebNN, especially around training? So the problem
For
with
training new models, not
Yes.
using models like you're showing. Yeah.
most of the hardware we have on desktops today is not for training, it's for inference. So AI is very different how you train things and how you actually run them. So the focus has been on inference, not like local training, so unfortunately.
Anyone else has a question? Let's see those hands raised.
You don't have to ask anything now. You can
Yeah,
always
exactly.
find me later.
Kenneth is going to be around, so
Yes.
Kenneth, give it up for Kenneth, everyone.